Okay, so last class, at the end, we were talking about sums of two random variables and how this affects the expectation and the variance. So let me remind you how that worked, and then we'll just continue on that thread for a bit. So this is a sort of brief review from last class. So if x and y are random variables, then we have a few things. The expectation, if we multiply by some constants, this would be alpha times the expected value of x and beta times the expected value of y. So it just means that what we have what's called linearity of expectation. And we can also say that the expected value of a sum is the sum of the expectations. When we look at variance, things get a little messier. So if x and y are independent, then we had that the variance of alpha x plus beta y was alpha squared variance x and beta squared variance of y. And the independence is necessary. I gave an example yesterday. Like if I were to take your exam score as x, and then the points you lost, 100 minus x as y, then these are both random values. Your exam score has various possibilities, and 100 minus your score does as well. But when you add those together, you always get 100. And so it doesn't vary at all. So that's an example where if things are not independent, the variance might even be as low as 0. So you always need to check or mention independence when you do the variance formula. Now let me put a little comment here on a common mistake. If we look at standard deviation instead, and we're going to be doing a lot of this today, the standard deviation, recall, is the square root of the variance. So I can plug in that formula we just saw. Square root of alpha squared variance x, beta squared variance y. Well, if I'm talking about standard deviation of that sum, I should talk about standard deviation of x and y, not variance. So we can replace that with alpha squared standard deviation squared of x, beta squared standard deviation squared of y. Now, so far, so good. Where many people go wrong is that they have seen the linearity of expectation here, this right here, linearity of variance and expectation. So you saw the expected value of a sum splits up. With variance, it splits up. And some students will decide that the standard deviation does the same thing. So when they see standard deviation, they'll write something like this, maybe with just alpha. That's not true. So the square root of a sum, you can't split this up. This is the final answer. We'll see some examples soon where if the two sigmas are the same, we can simplify them. But if they're not the same quantity, then you can't do better than this. This is just where it ends.
Excuse me, Professor.
Yeah.
For sigma squared of x and sigma squared of y, is that like sigma x all squared?
Yes, sorry.
Okay. All right, so that would just be this standard deviation squared.
Correct.
Okay.
If you wanted to make it feel linear, you could take this square root and square it, and then you'd have sigma squared is alpha squared, sigma squared, beta squared, sigma squared. But yeah, if you write standard deviation, you just get a messy thing, and that's just the way it is. But yeah, as you asked, sigma squared means the square of the standard deviation, which really is the variance. And one other comment to put down here, which is not a new thing, it's just reminding you of something from last class. If we have alpha x plus beta without y, then that linearity of expectation still works. But when we look at variance, you just get the alpha squared term. So the beta goes away. And the reason for that is that we could rewrite this by setting y equal 1. And in that case, that beta could become beta y, because y is always 1, so I haven't changed the equation. Then what is the expected value of 1? It's 1. If everyone gets 1 point, your average score is 1. Then how much does the value 1 vary? It doesn't. It's always the same. And so this term would go away, and the EY would be a 1. So the part I wrote in blue here, I would suggest either don't write it or write it on the side, because the point of the note here was to focus on the difference. And when we start throwing the y's in all over the place, it makes it look like the earlier work. So that was just an explanation, but you want to make sure to have a version that just looks like this at some point, so that when you look at this later, you can quickly notice that when you add a constant, that constant goes away in the variance. And since I'm putting notes here on things that might go wrong, I'll write down what I said earlier about when they're dependent. So if x and y are dependent, nothing is known. So cannot say anything. About variance. Now with expectation, that's fine. So that's one of the nice things is that expectation, that formula works even if they're dependent. It's only variance that does funny things. So are there any other questions about these formulas from last class before we go on and start working with them some more?
I just have a quick question. So when you say you can't reach any conclusion about variance, so like it's just you can't find the variance or the standard deviation if they're dependent. Is that what you're saying?
Maybe my statement's a little too strong. So if all that you know is the variance of x and the variance of y, then you can't do anything. If you knew the distribution of x and the distribution of y, then it would be possible to find the distribution of that sum.
Oh, so you couldn't derive any other information just with the variance and deviation.
Right. In order to derive any information in this case, you would need to know the actual distributions or something that we aren't learning called the covariance. So if you knew the covariance of x and y, then you would be able to reach all the conclusions you want. So there's another formula here that adds a term called covariance. But like I said, we aren't learning that in this class. It's another one of those cases where if you took the math major version 4070, you would learn covariance, but we don't. So there's an extra term when they're dependent.
And just for the sake of me making sure I get this down in my notes,
Yeah.
So if only the variance or the deviation is known, and the x and y are dependent, no other information can be derived.
Correct.
Okay.
If you know the PDF or if you know the covariance, then you can derive everything that you want. But in the absence of that information, you can't. The covariance is discussed in our book. If we have some time, I might mention it at some point, but I don't think I'll do that. Let me move this up here so we can do some work with it, but still have the formula sitting around. Okay, so let's suppose that a passenger is getting on a plane and the airline wants to figure out some information about what the combined weight of the person and their luggage will be. So a typical passenger on a flight has an average weight including their clothes of, let's say, 190 pounds, which is maybe too much, with standard deviation of 25 pounds. And then they also have luggage. That has an average weight as well. Now, if somebody has a suitcase, it's going to weigh a lot, but these days, most people don't bring a suitcase because it costs extra money. So let's say an average weight of 25 pounds. Most people don't carry that much on them, but if they had luggage, they would probably have more. So average weight of 25 pounds with standard deviation of 10 pounds. If the weight of the passenger and their luggage are independent, then let's find the average weight and standard deviation of the weight of this passenger and their luggage. So find the mean and standard deviation of the combined weight. That would mean passenger plus luggage. Now, the suggestion that they're independent may or may not be accurate. Presumably, somebody who weighs less, probably their clothes are lighter as well because they're wearing less. And somebody who weighs more maybe is taller or wider, and so their clothes weigh more. But let's assume they're independent so that we can do some calculations. Okay, so a good starting point would be to take all of these words and write it symbolically. So can somebody take that information about the passenger and suggest a way that I can write it using the notation we've been learning recently? Basically meaning the kind of notation on the screen right now.
So E of X is going to represent the passenger's weight on average. So it'd be E of X is 190.
Okay.
And sigma X, or the standard deviation, is 25.
And then what is X representing, you said?
X would just represent a person's weight,
Okay.
but I don't know how to say that in numbers.
Well, it's
Oh, we
not
can
a
just write it.
number, it's the weight
Oh.
of the passenger.
Okay.
Now,
And
a
then,
typical flight has a couple hundred passengers, and that's what makes this a random variable, because
Right.
the person shows up, we don't know what their actual weight will be ahead of time.
And then we just do the same thing for the luggage, but use Y.
Okay. And then EY is, I'm saying this is Y, and that was X. So EY was 25 pounds, and sigma Y is 10 pounds. And then we're looking for the weight of the passenger and luggage combined. So how do we write that in terms of these variables? So what quantity is it that we want to look at here? Maybe somebody else?
Are we looking for the E of alpha X plus beta Y, or just the E of X plus Y?
Okay, so X plus Y. So we want to find Z equals X plus Y, which would mean alpha is 1 and beta is 1. So even though I don't have an alpha and beta there, you can just say, well, they're just 1. And so as you said, we're looking for E of that. So what is the expected value of that sum?
Wouldn't it just be 190 plus 25?
Yeah, and you were getting that answer by using the additivity of expectation. So 190 plus 25 would be 215. So if this data were accurate, then the average combined weight of a passenger with their luggage would be 215. And then I don't want average again. So the data is almost certainly not accurate because children weigh less, but that's not important. So now if I want sigma of x plus y, okay, I have to answer that in case it's my kid's worker. 1 second. Hello? Hi, I'm fine. Oh, you are? Okay, I'll bring that in a minute. Thank you. I need to go for like 5 minutes to bring my kids to their social worker, like I mentioned earlier. So sorry, just be a 5-minute break. Okay, sorry about that. So back to looking at expectation and variance. So when we get to the standard deviation, we have a choice. If we want to just work with standard deviation, then, whoops. Then we could work with this formula, but that's an extra thing to learn. So if you're writing everything down, fine, you could take this formula. If you're like me and you don't want to remember too many things, then we could instead do sigma squared, because we know that's variance, and just square root it at the end. So either approach is fine. So like I said, like that, I usually do the variance version. You're fine using either, but I'll do sigma squared just because that's what I like to do. Then the linearity of variance tells me this is sigma squared x plus sigma squared y. But I mentioned that we do need to think about independence. So this is because x and y are independent. If you do not mention independence, then there will be some sort of a deduction because I can't tell if you just throw this formula out all the time or if you're aware of the limitations. This question stated they were independent, so you don't need to justify that claim. If it didn't say they were independent, then that would be extra work. Okay, well, sigma of x was 25. Sigma of y was 10. Adding these together, we get a big number. So 25 squared plus 10 squared is 725. And so the standard deviation of that sum would be the square root of that. Which is 26.9 pounds. Whoops. If we wanted to write units along the way, technically the units of the variance are pounds squared, but that's a little bit confusing. So the average weight of a passenger and their luggage would be 215, and the standard deviation would be about 27 pounds. Okay, are there any questions on the calculations that we just did? Because after this, we're going to do a bigger version of this. Okay, well, if you do run across any questions, maybe looking at it over the break or whatever, then you can ask after we have a break. Now, an airplane flight doesn't just have one passenger, they have a lot of passengers. So if a flight has, let's say, 150 passengers, then the average weight of the airplane won't be 215 pounds. It would be 150 people times that. But the standard deviation is going to be very different. So I'm going to do some other calculations on another screen now. And the goal of those calculations is going to be to come up with a formula that we can use with sums. In this particular case, like I said, if we have 150 passengers, the airline is going to want to know how much do they weigh and how much certainty is there about the combined weight of 150 people. So just put a note on the bottom here, but we won't do the work yet. So if there are 150 passengers, then what is their total weight? The reason for adding the passenger and their luggage was to get a more accurate measurement of how much weight is on that flight. And then how certain are we? And at the moment, certainty means standard deviation. After the break, I will talk about how we use standard deviation to find some notion of certainty. But for the moment, it's just a number we'll calculate. So what we're looking at now will be the mean and standard deviation of a large sum. So I'll call this the sum of many independent variables. The particular term that is commonly used is independent, identically distributed, random variables. And there's a shorthand that can be used for this. Which is that we call it IID. So if you look at topics in which we are talking about repeated experiments, repeated passengers, any situation where you have the same sort of thing occurring in many cases, they sometimes say IID random variables. And it just means you have basically many copies that look the same. Passengers aren't all the same person, but their weight distribution will be similar. So how will I write that out? Let's let x1, x2 to xn be IID random variables. With a certain mean, mu, and standard deviation, sigma. So in the example we are looking at, these might be a bunch of passengers. The passengers have an average weight of 190 pounds, or when we looked at the combination with their luggage, they averaged 215. And then they had a standard deviation. When we looked at this with luggage, the standard deviation was about 27 pounds. And we'll consider two different things. We'll consider W, which is going to be the sum of these. We add them all up. And we'll also consider the average, which is what you get if you add them all up and then you divide by n. And in the examples we've been looking at, this is like saying the total weight of all passengers. And the second one is like the average weight. And they're closely related because if you take the total weight of everyone and you divide by n, you get the average. But when we look at the standard deviation, we're going to find that they behave somewhat differently. So we're going to start by looking at W. So let's find the expected value of W, the total. So that's the expected value of adding all these up. And we've learned that we have linearity of expectation, or the expected value of a sum is the sum of the expectations. So I can divide this up into EX1, EX2, and keep on going to EXN. For example, by linearity of expectation. You might notice that our original formula only involved 2 variables. If you are concerned about that, what you can do is take x1 and then the big sum after it. And that's 2. Now you have 2 terms. You have x1 and you have a sum. And then you can take that big sum, pull out x2 and have a smaller sum. And you can keep on repeating this. So if anybody really wants to know how to get from the case of 2 to the case of many, I am just basically pulling pieces out. So pull out x1, then pull out x2, and so on. Now these were IID, meaning recall that they all have the same distribution. And so the expected value of x1 is the same as x2, is the same as x3, and so on. Like when we looked at airline passengers, it would just be saying, if all I know is the passenger number, not their identity, then my expected value for passenger 1's weight is around 190, and the same for passenger 2 and 3, and so on. So this is going to be mu plus mu, and I keep getting mu all the way out to the end. And there were n of those, so that would be n times mu. So this has shown that the expected value of W was n mu. And if you prefer to see that in terms of single variables, we could write that as EW is n times E of x1. This formula is only true if all of them follow the same distribution. So if I were to look at passenger weights and consider men and women separately, they probably have different distributions. If passenger 1 was male, it wouldn't be reasonable to say that I take the average weight of a man and multiply it by n. And it would be even more extreme if we had kids separated as well. So if I had men, women, and children all separate, then I wouldn't take the weight of a child and multiply it by 150 to get the whole flight. I would have to look at how many kids, how many men, how many women. But here, we haven't separated it by age or gender. We just have passengers as a big population. The next thing we need to do is look at the variance. This. So now we're going to do the same thing, but with variance. Or you can think of it as standard deviation squared. So the variance of W will be the variance of adding all these up. And these are independent, so I can add up the variances. And like I said earlier, you always need to mention when you use independence. Don't just automatically write independent all the time, because I could give you a problem where they're not independent, and the right answer is cannot be determined because they are not independent. But in this case, we were told independent at the top. Since they're identically distributed, they all have the same distribution and the same mean and the same variance. So how can I get the variance of x1 from the information that was provided here up at the top? So this is what you were provided, not variance. Any suggestions on how to take the information in that passage at the top and give the variance of x1 from it?
Would doing it with the standard deviation squared thing work?
Okay, correct. Yeah, so variance is the square standard deviation, and we just have this repeated. There were n of those terms, so this would be n times sigma squared. So we can reach a conclusion again. Well, since I wrote sigmas in my final answer on the right, I may as well state my results in terms of sigma as well. So I'll state this twice. I'll state it with variance and I'll state it with sigma. So the variance of W we found was n times the variance of one term, or actually I'll follow the pattern I did up above, which was that I wrote the concise formula on the left and the other one on the right. Okay, so the more concise one on the left side, so variance is standard deviation squared. So sigma of W would be the square root of n sigma squared. Or if I wrote it in terms of variance, I would get that other formula.
Professor, is that the square root of n times sigma or the square root of n times sigma? Sorry.
Yeah, I'll put parentheses there just to make that clear. So I was taking this n sigma squared formula and square rooting it, because the left here is sigma squared of w. So if I square root that, only the n gets a square root, and that square goes away. So these formulas tell us how to find the mean of a sum, like the total weight of all passengers, and the standard deviation or variance of that sum, such as if we needed to look at how much the weight of all passengers varies. Now, naturally, we might want to look at X bar as well. W was total, but in many cases, we're interested in averages more than totals. So for example, if I talked about exam scores, nobody really cares what you get if you add up everybody's score on exam 1. There's, I don't know, maybe there were 25 people who took it. Well, adding up all your scores gives a number that's a couple thousand, but that's not very helpful. Saying that the total, that if I add up everyone's exam scores, you get 2,000, doesn't help you understand how well each person did. So with airlines, total weight is what matters because that determines the weight of the plane. With something like exam scores, the average is what's important. So let's go through here and figure out how to adjust these formulas if we're looking at averages. So if I was looking at X bar instead, then I have E of X bar. And I can write this out. Let's see, that's E of X1, X2 to Xn divided by n. If I wanted to, I could break this up into 1 over n times x1, 1 over n times x2, 1 over n times x3, and so on. But does anybody see a way that I can get the n outside of the expectation? That way I don't have to redo everything. If I can pull the n outside, I can use my answer with w. So how can I get n outside of that expectation?
You would use 1 over n and just pull it out of the...
Yeah, so the linearity of expectation says if you have constants, n doesn't look like a constant, but it is. It's how many people were in my sample. Then you can pull it out front of the expectation. And now that right-hand side was E of W. So this is 1 over n EW. And we know that that's n mu. So putting this all together, this tells us that the expected value of your average is just mu. And if I wanted to write that in terms of x1, I could say that equals E of x1. This should be almost obvious, meaning if I had not put all the symbols on the screen and I had asked you this as a word problem, you might have got the answer. So my word problem here would be something like the average weight of a passenger on a flight is 190 pounds. If I average the weight of all 150 passengers, what should I find? You say, well, you just told me it's 190 pounds. So that's the answer. So that's all this formula has said. If I tell you the average weight of a passenger is 190, and then I tell you I average 150 people, well, then you expect me to get about 190. Now, what about when we look at standard deviation? And just like before, I'll start with variance just because we have a little more information on how variance works. So the variance of the average, well, that's the variance of x1, x2 to xn divided by n. And now, like last time, can anybody tell us how to get the n outside of the variance?
The same way.
Okay, so what would I put in front of that? Sounds like you're saying something.
1 over n.
Okay, so I'm glad that you gave that answer. It's actually wrong, but I'm glad you gave that answer because on the exam covering this material, usually about 2/3 of the class put a 1 over n. So with variance, recall that variance is squaring everything. In fact, the definition was the expected value of x minus mu squared. And so since the variance is squaring everything, that 1 over n gets squared as well. And that was because of the formula that said the variance of alpha x was alpha squared variance x. So like I said, I'm glad that that was the answer given because maybe this will help people not make that mistake when there's an exam. So make sure that constants get squared when you take them outside. So we have 1 over n squared. And that right-hand term now is the variance of w. On the left, we can see that that is going to be n times the variance of one term. Well, the n on the top cancels one of those on the bottom. So the variance of x bar is 1 over n times the variance of one term. And I was writing that in green before, so it's not terribly important. Let me just be consistent. So that's that means that as far as variance goes, when we average n terms, the variance also drops by the same factor. There are 150 people involved in my flight. The average weight of each person varies a certain amount, but if you add up a lot of people, the fluctuation will drop. Now, standard deviation is usually the more interesting quantity. Standard deviation is the square root. So I would have 1 over square root of n. The square root of the variance would be sigma. So when we look at the standard deviation over a large group, it decreases by 1 over root n. When we look at the variance, it goes down as 1 over n. But as has been mentioned many times, standard deviation is the quantity that is more relevant to using statistics. And the reason for that went back to my discussion about distance. The distance between 2 points in 3D space involves a square root, not a square. So the standard deviation is like distance. So distance, in a sense, goes down by 1 over root n when we're averaging, but 1 over root n when you average, but up by root n when you add. So the total of 150 people is 150 times 1, but the amount the total varies only grows by the square root of 150. And this actually turns out to be the key of why statistics works, because it means that if I take a large group of individuals and I look at their average behavior, it doesn't vary a lot. So individual people's weight may vary a lot, but if I take enough people in a sample, the 1 over root n is going to make this amount very small. So take a lot of people, divide by n to get an average, and it tells me that the standard deviation will decrease until it gets small. So let's apply this to that airline problem. So we'll go back and think of our airplane. The airplane data, we found that if we look at a passenger and their luggage together, it averages 215 pounds. So average weight of a passenger and luggage is 215 with standard deviation sigma of 26.9. The airline wants to predict how much the total weight of passengers and luggage is going to be. Why would they do that? Well, airlines don't just fly passengers and luggage, they actually sell their unused cargo space and unused weight. So if an airline believes they're going to have 5,000 pounds of spare capacity, they're going to sell that, meaning they're going to go to some shipping companies and say, you can put 5,000 pounds of your products on our plane in the cargo hold and pay us a certain amount. So they need to know ahead of time how much spare cargo they're going to be able to take. So let's find, whoops, I didn't say the number of passengers. If there are 150 passengers, then determine the expected total weight and standard deviation of that total. And the airline doesn't really care about averages, they care about totals. Again, because their plane can carry a certain amount of weight and they want to know whether they're going to have 5,000 pounds of spare capacity at the end. Okay, so we need to decide which of all these formulas get used. So do I want to look at W or X bar?
W.
Yeah, so since we're looking at totals, then it's W. And now the formula we have at the top is that E of W will be N times mu. And mu is 215, so this is 150 times 215. That's 32,250 pounds. And then the standard deviation of W, well, the W formula says take root n times sigma. So root 150 times 26.9. Which is 329.5 pounds. So I'll just round it to 329. Notice that originally the amount a passenger's weight varies is about 1/8 of their total. So the standard deviation is a significant fraction of mu, 1/8. Now, the standard deviation is only about 1/100th of the total weight. So that tells you that even though individuals' weights may vary significantly, in this case by about 12%, when you look at a large group of people, then the total weight does not vary much at all. Here, the standard deviation, again, was only 1% of the total. So so let me give you a couple more terms that we use for some of the quantities we've looked at here. So when we're looking at a total like W, we found what the mean is. That was simple. And then we had our standard deviation formula. And the standard deviation is called the standard error. Let me go up to there and mention that. And that means that when you are looking for your total weight, the standard error tells you something about how much it changes. However, usually when we do standard error, we're talking about averages. So the average version is usually what you're looking for. So if you just see the term standard error, it probably means average. So I will distinguish between them here by calling this other one standard deviation of a total. So standard error of the total weight is root n times 1. Standard error of the average is 1 over root n times 1. And when we start talking about sample data, then this term standard error will make even more sense because it's going to tell us how far away is our sample data from reality. If I take the average of 150 people, it might be off by 2 pounds or 50 pounds. And obviously having an error of 2 pounds is better than an error of 20 pounds. Okay, are there any questions about stuff that you see on the screen right now?
Yeah, so is that pretty much like saying the total is 32,250 plus or minus 329?
It's going to turn out that usually you use 2 times that standard error, but almost, yeah. So what we'll talk about after we have a break is that there's a 95% chance that what you get is within 2 standard errors of the mean. So in this case, if we're looking at the airplane, they can be 95% certain that the total weight of passengers will be within 650 pounds of that total there. If you add and subtract the standard error, it's a 68% chance, so about 2/3. So about 2/3 chance of being within one standard error and 95% chance of being with two. But I'll write that down after we have a break. Something called the empirical rule. So on the syllabus schedule, you'll see the empirical rule somewhere. That's probably the first topic listed for today, but I'm kind of finishing up stuff that was scheduled for last class. Okay, so it's 11:55. Why don't we take a break for 10 minutes? And at 12:05, we'll come back and talk about empirical rule and be addressing the question we had a minute ago of how certain we are that we're within one standard deviation. Okay, so take a break till 12:05.